Hi, everyone. Today we're going to be talking about a topic I find really interesting. This is going to be about efficient matrix multiplication. Now, by this point in linear algebra, you already know how to multiply matrices. We've talked about that. And this is going to look at it in a little bit of a different way. I'll tell you that this topic is not in our linear algebra textbook. This is an extra topic that I'm adding myself. And yeah, so let's get started and let's see what this is all about. So before we can talk about efficient matrix multiplication, I want you to do a quick warm-up problem. I want to make sure that we remember how to do standard matrix multiplication. So go ahead and give this a try. I would like you to find the product of this 2 by 2 matrix times another 2 by 2 matrix. All right, so you could pause the video for a minute and try this out. All right, so what you should have found is, remember how we do this? We use rows and columns as appropriate. So we're going to use the first row and the first column of these two matrices, the 4, the 2, the 7, the -3. We've done this a bunch of times. So we want 4 times 2 plus 7 times -3. That's going to get us the entry in the upper left. For the entry in the upper right, we use row 1 of the first matrix and column 2 of the second matrix. So 4 times -1 plus 7 times 0. And continue to get 1 times 2 plus 3 times -3 and 1 times -1 plus 3 times 0. All that's left to do is simplify this. So you do these multiplications and you do these additions, and you wind up getting -13, -4, -7, -1. So that's the answer. We multiplied 2 by 2 matrices, and we got a 2 by 2 matrix as the result. So if you think about how we actually did this, it's really just a bunch of adding and multiplying numbers, right? It's a bunch of arithmetic. 4 times 2, 7 times -3, add them together. Any other method that we come up with to multiply matrices needs to get the same answer, right? So in this lesson, we're going to learn another method, but it needs to get us the same answer still. Let's talk in general about matrix multiplication. And for right now, we're going to focus on this 2 by 2 case. So in general, if I want to do a 2 by 2 matrix, let's say it's called, the entries are A, B, C, D, and I'd like to multiply it by another 2 by 2. We'll call these entries E, F, G, H. You know that when you multiply them, you wind up doing AE plus BG, AF plus BH, CE plus DG, CF plus DH. That's basically what we did above, except instead of specific numbers, we just have these constants, A, B, C, etc. In other words, if we call the first matrix capital A, and it consists of these entries, and we call the second matrix capital B, and it consists of these entries, then the product, A times B, is going to equal a third matrix, C, where C equals, instead of continuing through the letters of the alphabet, I'm going to call this lowercase c11, c12, c21, c22, such that we can find all of those C's We said above that C11 is AE plus BG. C12 equals AF plus BH. C21 is CE plus DG. And C22 was CF plus DH. And when we write it all out like this, we're kind of describing the algorithm, breaking it down into all the little steps. You want to find the 4 entries of C. You do it by finding them in this way. And look at what we're doing here. This is a bunch of additions and multiplications of real numbers, right? Scalars. Like A times E is a multiplication of 2 real numbers. B times G, multiplication of 2 real numbers. And then we've got a bunch of plus signs. How about this? I'm going to summarize this by saying that this strategy requires, at the heart of this method, at the core, like what are we really doing? We're doing 4 additions and 8 multiplications. It's just a bunch of arithmetic. So the 4 additions that we're doing are the 4 plus signs that we wrote. Plus, 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 plus. And the 8 multiplications are AE, BG, AF, BH, and these other ones. So we just summarized how to multiply 2 by 2 matrices. Now, in computing, like if we wanted to program a computer to multiply 2 matrices for us, this is kind of a good summary of the algorithm. You could tell a computer to do these additions and multiplications and get the answer. But in computing, multiplication is considered expensive. I'm putting that in quotation marks. Addition or subtraction is easier. So what I'm getting at here is really a discussion of computational complexity. You know, when you want to have a computer do arithmetic for you, addition is a much faster process, and multiplication is a little bit slower. So if we want to do this as efficiently as possible, a computer might get bogged down doing a bunch of multiplications, especially for large numbers. So here is a question. Can we do AB equals C with fewer than 8 multiplications? Because maybe in a certain sense we could find a way to do this more efficiently if we didn't have to multiply so many numbers. And you might be saying, well, this is just how matrix multiplication is done, right? This is how matrix multiplication is defined. Why should there be any other way to do it? But let's ask ourselves, you know, could there be another way to multiply 2 general 2 by 2 matrices and still get the correct result? It still has to get the same result, C. And we're not saying like, oh, what if the matrix has like a 0 in it or something like that. We're still saying that they're general 2 by 2 matrices. So this question was answered in 1968 by Volker Strassen, who published this paper, Gaussian elimination is not optimal. You don't need to worry about reading all this right now. I'm going to kind of tell you the summary, but Volker Strassen in 1968 found a different way to multiply matrices. And this was kind of a surprise to everyone because everyone just had assumed that there was just the standard way of multiplying them, and why should there be any other way? This was actually a very short paper. He introduced an algorithm. and he summarizes the algorithm. Now, I've posted this paper as a PDF in the usual place where I post worksheets. So go ahead and you can look at it there. But I'll tell you some of the highlights. There's actually that paper and one other paper that we're going to discuss later. So this is known as Strawson's algorithm. Let's go ahead and start a fresh sheet of paper. Strawson's algorithm. For answering this question. And it can be thought of as just a two-step process. We're going to say step one, Strawson says that we should compute 7 constants. There's going to be an M1, M2, M3. All right, it's going to be 7 of these. I'll start writing what they are. And you don't need to memorize these or anything like that, but they're going to be based on the entries of the matrices A and B. So this is going to be A plus D times E plus H, C plus D times E, A times F minus H, D times G minus E. I certainly don't have these memorized, so I have to refer to the paper. M6 equals C minus A, E plus F. M7, B minus D, G plus H. So step one is compute all of these. We're assuming that we know what the matrix A is and we know what the matrix B is, so we can compute all of these. Step two is to compute C11. C11 is one of the entries of the product, right? We're trying to find the matrix C, and we said it was C11, C12, and so on. So C11 is going to turn out to be M1 plus M4 minus M5 plus M7. C12 is going to be M3 plus M5. C21 is M2 plus M4. And C22 is M1 minus M2 plus M3 plus M6. Wow. So this might look very strange. All right, but the result of this doing this is AB equals C, where C is that matrix C11, C12, C21, C22. It gets the correct answer. All right, how do we do it? I mean, computing M1 is adding some numbers, multiplying some numbers. M2 is adding, there's some subtraction in here. And then after we've done all of these computations, we do all of these computations. There's adding, subtracting, adding. And you might say, like, is this really more efficient? Didn't I say this lesson was called efficient matrix multiplication? This kind of looks more complicated. However, this is found with only 7 multiplications. And we said earlier, from a computational standpoint, multiplication is considered to be more costly, and addition and subtraction is considered to be easier. What this algorithm does is it gets the correct result. Only 7 multiplications, but it does more addition and more subtraction than you would usually expect. By the way, do you see what the 7 multiplications are? I'll point them out for you. The 7 multiplications that we're doing, here's one right here, M1. That's a multiplication. M2, each one of these has a multiplication. M3, M4, M5, M6, M7. So each one of these has exactly one multiplication of real numbers. So you do some adding, subtracting as appropriate, and then, yeah, you do these 7 multiplications, you do some more addition and subtraction, and you just found a matrix product with only 7 multiplications. Now, note, so far, we've assumed that A and B are 2 by 2. And this entire time, you might be thinking, like, well, what's the point of doing all this? Multiplying 2 by 2 matrices is pretty easy. We can do it by hand, so a computer should be able to do it really quickly, right? And we did a warm-up problem at the beginning of this lesson, so we know how to multiply 2 by 2 matrices very fast. Well, it turns out that Strawson's algorithm can be extended to the more general n by n case. And I'll tell you how. I'll tell you how it can be extended, because right now it seems like a 2 by 2 algorithm. So how could we use Strawson's idea to multiply larger matrices? That's really where Strawson's algorithm is going to help us. Because what if we had 2 very large square matrices and we wanted to multiply them? That's something that might take a while to do by hand. Or if the matrices are really large, it might take a while for a computer to do it. So if you could find a way to get the computer to do it with fewer multiplications, that might be better. So in order to extend this idea to the larger cases, we're going to use a concept called block matrix multiplication. Block matrix multiplication is something we haven't talked about yet in this course, and it actually has other uses as well, but it's going to help us here for what we're trying to do. So suppose we want to multiply 2 4 by 4 matrices. I'm still keeping the examples kind of small just so that we can easily see it. Let's just look at a 4 by 4 case. The idea behind block matrix multiplication is that we can write them, the 4 by 4 matrices, we can write them as A, B, C, D. These are uppercase letters, and E, F, G, H. You know, we usually use lowercase letters for scalars and uppercase letters for matrices. Well, we're going to write these 4 by 4 matrices so that they look like this, where the uppercase A, B, C, all the way up to H are each 2 by 2 matrices. So you see this first matrix I wrote out, A, B, C, D. Each one of those entries is actually a matrix that's 2 by 2. So you have a 2 by 2, 2 by 2, 2 by 2, 2 by 2. All together, it's 4 by 4. That's the concept of block matrix multiplication. It's like A is a block, B is a block, C and D. Well, if you do this, and then you want to multiply the 4 by 4 matrices, it turns out that you can actually multiply the blocks like the way that we would usually do matrix multiplication, you know, AE plus BG, AF plus BH, and so on, except instead of these things being real numbers, these things that we're multiplying are each 2 by 2 matrices. This is probably not how we would multiply 4 by 4 matrices by hand. Like if we were going to just do it by hand, we'd use the standard method maybe. But remember, I'm just using this to kind of illustrate the concept. This could actually be extended to much larger cases as well. So what's going on here? This has 8 cases of 2 by 2 matrix multiplication, I'm going to abbreviate that, where each one has 8 multiplications. If we're using the standard definition, the standard method to multiply A times E, like we did earlier, there's 8 multiplications and 4 additions. So there's 64 total multiplications of real numbers. Now, what does this have to do with Strawson's method? What can Strawson's method do? We can use Strawson's algorithm in this block matrix multiplication problem. And in that case, we have, instead of having 8 cases of 2 by 2 matrix multiplication, we have 7 cases of 2 by 2 matrix multiplication. Each with 7 multiplications of scalars, for a total of 49. So it's like Strawson's algorithm nested inside Strawson's algorithm. We would use it on each of the individual pieces, and we would use like the blocks, and we would use it overall. So yeah, we wind up with 7 times 7 multiplications instead of 8 times 8. So this is where you start to see some of the maybe cost savings, like if we think of multiplication as being a costly process for a computer. Maybe this is more efficient for a computer to answer this problem with 49 multiplications. Now, it would have a lot of extra additions and subtractions. But the idea is that for a computer, adding or subtracting numbers is almost trivial. Adding or subtracting numbers is super easy, super fast. We'd like to trim down the number of multiplications, and that's what this does. Now, I said this could be extended for the n by n case, and what I just showed you was the 4 by 4 case. So we went from having 64 multiplications to 49. Let me tell you that for the n by n case, let's compare the efficiency, like the number of multiplications that are needed. So I'm going to look at different values of n, and we're going to make a little table here comparing the standard method with Strawson's method, or Strawson's algorithm. Now, I've already told you that for the 2 by 2 case, the standard method uses 8 multiplications, Strawson's method uses 7. And we've just discussed how for the 4 by 4 case, the standard method would have 64 and Strawson's method has 49. So it seems like we're seeing the benefit. It turns out that for 8 by 8 matrix multiplication, the standard method would have 512 multiplications. and Strawson's method has 343. So you see, the larger the problem gets, the more we benefit from using Strawson's method. By the way, for 8 by 8, the way you would do it is you would subdivide into blocks that are each 4 by 4, and then you would subdivide those blocks into blocks that are 2 by 2. So kind of a nested process. Kind of a recursion. So what happens when you get all the way to n, just being more general? Well, look at this pattern of numbers, 8, 64, 512. What we're really getting is n cubed. It takes n cubed multiplications in the standard sense. What do you think? What do you think we get here for Strawson's method? Like, what number am I going to put here? I'll show you some scratch work. I mean, maybe, can you see a pattern in the 7, 49, 343? They're all powers of 7. I mean, 7 is 7 to the 1 for n equals 2. The 49 comes from 7 squared. That's for n equals 4. The 343 is 7 cubed. That's what we got for n equals 8. So a general formula for, just some positive integer n, 7 raised to what? Something involving n. I'd like you to think about this. See if you can figure out what goes in this question box based on this pattern. These are powers of 2, right? And the 2 kind of corresponds to 1. The 4 gets us 2. The 8 gets us 3. It's like we need to undo the power. How do you undo a power? The inverse of exponentiation, the inverse is a logarithm. So this turns out to be 7 raised to the log base 2 of n. And you can check that. That does get us the 7, the 49, the 343, and so on. Now, you might look at this and say, wait a second. I said this was going to be the general n by n case, but everything that I've shown you is a power of 2. And you might say, well, what if n is not a power of 2? Well, then I'll tell you that these results are approximate. So if n is not a power of 2, then there are a few options of how to deal with it. We still would like to do some kind of block matrix multiplication to break it up into pieces. I'll tell you the simplest option. The simplest option, if you have something like a 7 by 7 matrix times another 7 by 7, the simplest option would be to pad it with an extra row and column of zeros so that it is a power of 2. All right, and you can always do that. Like if you have 100 by 100 matrices, you could add extra rows and columns of zeros until they become 128 by 128, because those are powers of 2. And then you could use the block matrix multiplication like we've been doing. That's one way. That's one option. A smarter option is to subdivide and do block matrix multiplication anyway, and then at the lowest subdivision, the matrices will be small enough that you could just do them with the standard method. So the main thing I wanted you to take away is that it does still work, even if it's not a power of 2. It's just that these comparisons would just be approximate then. Now let's talk more about efficiency and how the standard method and Strawson's method compare. So efficiency. And we are focused on the number of multiplications needed. And by that, I mean the number of multiplications of real numbers. How does n cubed compare versus 7 to the log base 2 of n? They seem like very different expressions, so how can we compare them? How do these compare? And in particular, how do these compare when n is large? Because we want this to be efficient for large problems. We've already said that if a problem is like 2 by 2, we can just do it by hand. What we're really interested in is larger problems. In order to see how these two numbers compare with each other, I mean, you could call them functions. You could say these are two functions of n. So to see how these two functions compare with each other, here's an idea. Let's try to write 7 to the log base 2 of n as n to the p for some number p. Like I basically I'm saying that I'd like to try to get both of these expressions to be in the same form, and then I could see how they compare with each other. Because if we claim that Strasson's method is more efficient, it has fewer multiplications, then I think that this exponent p is going to be smaller than 3. But how much smaller than 3 is it? So here's what we'll do. Here's the form that I want, and here's the form that I have. Do you think we can solve? Do you think we can solve for p? This is kind of an interesting, maybe algebra question. You learned about logarithms a long time ago, and you probably learned how to solve exponential equations. So one idea is take logarithm base 7 of both sides. So we're doing a little bit of algebra or maybe pre-calculus. Log base 7 of both sides is, and then on the left-hand side, the p can come out front. That's a property of logarithms. And on the right-hand side, we get log base 2 of n. This works out because we can solve for p in terms of n. We get log base 2 of n over log base 7 of n. Does that help us, though? I mean, I said we wanted to try to find what p is, and I guess we did. All right, so we can go further with this. There's a cool trick that we can do here. Do you remember at some point, I'm sure you've seen this at some point, here we teach this in pre-calculus. There is a formula called the change of base formula. The change of base formula from pre-calculus, here I'll write it off to the side, change of base formula. Back when you learned about properties of logarithms, this one was probably mentioned. It probably wasn't used very much. It's probably just kind of mentioned and then used once and then you never saw it ever again. But now we're using it. The way that we usually say it in pre-calculus is something like this. All right, this is a property of logarithms that a log base a of x is equal to log base b of x over log base b of a. So by the change of base formula, if I have log base 2 of n over log base 7 of n, I can actually change this to log base 2 of 7. And that is much nicer because it doesn't have anything unknown. There's no n's in it. It's just a number. So that's kind of a cool use of the change of base formula. And by the way, log base 2 of 7 is approximately 2.807. told you that I was expecting this to be a number less than 3. So where are we at with all this, comparing the efficiency? So what have we figured out? There are n to the 2.807 multiplications instead of n to the 3. If we use Strawson's algorithm, generalized for the n by n case, instead of the standard algorithm. So do you think this is much better? 2.8 compared to 3? It doesn't really seem like it's that much better. Like, what's the big deal? Well, let me show you an example. I said that we want to use this on large problems. So suppose A and B. I'm going to go with a power of 2 just for convenience. But suppose that the problem is this size. You're trying to multiply matrices that are this big, 1024 by 1024. The standard method, how many multiplications are there going to be? It's going to be 1024 cubed. Okay, 1024 cubed is going to be this number. That many multiplications of real numbers. You see why I said that we would be trying to get a computer to do this for us? We're not going to multiply a billion numbers by hand. So if a computer is doing this for us, the computer would have to multiply a billion real numbers, like a billion pairs of real numbers getting multiplied. That's a lot of work. So with Strawson's method, we would have 1024 raised to the 2.807, and it winds up equaling this. Yeah, it's a very different number, right? This is much more efficient. We started to write a little table. You know, we had n equals 2, n equals 4, n equals 8. Well, I guess you could add this to the table for n equals 1024. This is where we really start to see the payoff. So Strawson's method would do vastly fewer multiplications to solve the problem. It would have a lot more additions and subtractions, but we're okay with that. By the way, if you had something that was not a power of 2, like let's say these were 1000 by 1000, I would probably just pad them with extra columns of zeros to make them this size. So it still works. So we still have more to talk about, but let's think about what have we said so far. So we started off this lesson by looking at how matrices are usually multiplied, the standard method. We did a little 2x2 problem, and then we introduced Strawson's algorithm and saw that it uses fewer multiplications. And that's what we really care about, because the additions and subtractions are pretty negligible as far as computing time. So if you've got really large problem and you want to have a computer solve it, a computer might have an easier time using Strawson's method instead of the standard method. Now, Strawson's algorithm, that paper that I showed you, was from 1968. And you might be wondering, is that the end of the story? Like, everybody did standard matrix multiplication. Strawson said, let's do it this way. People started doing it this way. Is that it, or is there more? So that's the question, is can we do better? Can we do even better than Strawson's method? So let's talk about this some more. So we're saying that the question is, can we do better? Let's say that A times B equals C, and let's assume that we're talking just about n by n matrices here. Okay? Let's say that it uses n to the omega multiplications. So we're giving this thing a name. This is the lowercase Greek letter omega. If we use the standard method, the definition of matrix multiplication, we've seen that we get omega equals 3. And if we use Strasson's, we've seen that we get omega equals 2. I shouldn't say equals. It's approximately equal to 2.807. Can we get this exponent to be even lower than that? Like with a more modern method, maybe? So let's move this other page away. Well, I'll tell you a couple of facts. All right, fact number 1. It is known that omega cannot be less than 2. No matter what kind of method you come up with, you can never get omega to be less than 2 because of the number of inputs and outputs in this process. Like, how many entries are there in A? How many entries are there in B? How many entries are there in C? Well, I guess you would say that if you considered all the entries on the left-hand side, there are 2n squared inputs. And on the right-hand side, there are n squared outputs. And because this is 2n squared and this is n squared, we need at least n squared multiplications because of the number of inputs into this algorithm. I'm not saying that omega equals 2 and that there's a method that does this with omega equals 2. I'm just telling you that if people keep searching for more better algorithms, you'll never find one where omega is less than 2. Now, fact number 2, in general, 2x2 matrices cannot be multiplied using only 6 multiplications. So the standard method uses 8, Strasson's method uses 7, and it has been shown that you will never be able to find a method that does it using only 6. The proof of this, there is a proof by Hopcroft and Kerr from 1971, and also by Vinograd in 1971. So Strasson came around with his method in 1968, and people started wondering, like, can we do this with only 6? And it was found that no, it is not possible to do with only 6. So this means if a better algorithm exists, it needs to be based on more than just 2x2s. So what happened is people started looking at larger cases. People started saying, what about 3x3 matrix multiplication? Is there a more efficient way to do that? And not using Strasson's algorithm, but just looking for a new algorithm from scratch. Is there like some really efficient way to multiply 3x3 matrices? Because if there is, then maybe we could, do block matrix multiplication, and that would help. And this leads us to another published paper. from 1975 by Julian Lauterman, an algorithm for multiplying 3x3 matrices using 23 multiplications. All right, so you're starting to see kind of the timeline of history here, where Strawson's thing was 1968. Hopcroft and Kerr proved in 1971 that if you wanted a better algorithm, you'd have to look at more than just 2x2. Lauterman's algorithm from 1975 is an algorithm for the 3x3 case. I've also posted this paper along with Strawson's method, where I usually post PDFs. Let's talk about Lauterman's method. And is it more efficient? Lauterman's algorithm from 1975. If you're given 3x3 matrices, A, B equals C, or larger matrices that are subdivided into 3x3 blocks. The standard method. Turns out, you could actually do a little 3x3 general problem and count how many multiplications you did. It turns out you would do 27 multiplications. And as we just saw in the title of that paper, Lauterman's method uses only 23 multiplications. Oh, and by the way, if you're wondering where the 27 multiplications comes from, that 27 comes from 3 cubed. So it's not just a coincidence that that's 27 for a 3x3 problem. Here's a question. You know how up above... All right, so here's where we're at with Strawson's algorithm. That does it in 7 multiplications. And then we had fact number 2 that said it actually can't be done using only 6. So that was kind of the end of the search for 2x2 algorithms. It was proved that you can't do it in 6, so people stopped looking for an algorithm that uses only 6. Lauterman found this that does 3x3 problems in 23, so people started looking to see, is there a method that can be done in only 22? Can 3x3 be done with only 22 multiplications? And the answer is nobody knows. Nobody knows whether it can be done. This is kind of an open question in math right now. Can 3x3 matrix multiplication be done with only 22 multiplications of real numbers? We don't know. I don't have an answer to tell you. I can tell you that it has not been proven false, but it has not been proven true either. It's an open question. Now, personally, I do think it is possible. I think that someday somebody will discover an algorithm that does this. And some of my colleagues also think that it's possible. But nobody's found an algorithm to do it yet. So, as of right now, we don't know. If you could find one, probably get an algorithm named after you, and then I would have to include you in this lesson the next time I teach it. All right. We were doing some facts earlier. Fact number 3. Since log base 2 of 7 is approximately log base 3 of 21.8, a 3x3 algorithm would have to use 21 multiplications to be more efficient than Strawson's. So you see, even though Lauterman's method is more recent than Strawson's, Strawson's is actually still the better one of the two. You'd have to find a 3x3 that goes all the way down to 21. And we don't even know if it can be done in 22. We don't know if it can be done in 21. People are still searching for new methods. Fact number 4, the 3x3 case is known to be impossible using 18 multiplications. So there's still a lot of room there, right? I mean, the true lowest number of multiplications for the 3x3 case is somewhere between 19 and 23. But nobody knows for sure which thing it is. Maybe Lauterman's algorithm is the end of the story for 3x3 cases. Maybe 23 is the best. Maybe 19 is the best. We don't know yet. Now, recently, people have been searching for better 3x3 algorithms, but people have also been looking at 4x4, 5x5, and also like weird hybrid methods that break matrices up into different size blocks and use other techniques. So they kind of go beyond just some of the basics that I've covered today. But I want to tell you some recent progress in this area. There has been progress since Lauterman's algorithm and Strawson's algorithm. So I'm going to show you a little table, kind of like a timeline of progress on trying to lower that exponent omega. So we're looking at the n by n case, and we're saying that AB equals C uses n to the omega multiplications. I'm going to tell you the year, the method, and the omega. All right, ready? First of all, we will begin, our story begins actually before all of this. In the 1800s is when the standard method was popularized, and in that case, omega is 3. Everybody used the standard method for a long time, and then in 1968, which I would really like to emphasize to you that that is really not that long ago in terms of how long people have been studying math, right? That's not long ago at all. Strawson's method, omega 2.807. So I told you about Lauterman's algorithm from 1975, but I'm going to skip that because it wasn't better than Strawson's. All right? The next better algorithm came along in 1978 by Pan, and it reduced omega down to 2.79. A small improvement. Well, but we've seen that when n is large, even a small improvement in omega might make a difference because it's an exponent, right? The next improvement was the next year, 1979. There was a method by Bini that lowered the exponent to 2.78. The next improvement was 1981. by Schoenhag. Schoenhag brought the exponent down to 2.55. So that was kind of a big deal. That is a significant improvement. And that same year, 1981, there was a method by Coppersmith and Vinograd that reduced the exponent to approximately, these are approximate numbers, 2.50. I guess I could zoom in on this. In 1987, Strassen strikes back with a method that brought down omega to 2.48. But that same year, later that year, Coppersmith and Vinograd again found a better method, 2.375. So you see there was a lot of progress in the 70s and 80s. This Coppersmith and Vinograd algorithm was considered to be the best for a long time. It was the best for a long time. And what I'm going to show you next is that there is a big jump in time. Big jump. Because the next improvement for efficient matrix multiplication was 2010. And this was by Stothers, who found a new method that brought the exponent down to 2.3737. Not a very big improvement, but an interesting improvement after all that time. And actually 1 year later, there was a method by Williams. Virginia Williams brought this down to 2.3729. So, I'll just tell you, since I'm telling you the timeline of this, that I learned about this kind of problem when I was in graduate school. And when I learned about this problem, I learned that this method by Virginia Williams was the best method that existed. And that was the end of the story. But stuff has happened since then. There's been progress. There was a new method in 2014 by Francois Legal. Brought the exponent to 2.37286. Look at that. Look how close those are. It was a small improvement, but an improvement nonetheless. I started teaching this topic in 2015, and I would tell students, that this method by Francois Legal is the best that exists. I've taught this a few times. And now, as of today, there is another method from 2020. I'm making this video in 2021, and this is the last known result on this list. It is a method by Allman and Williams. That's the same Williams as above. So Josh Allman and Virginia Williams have found a method that reduces the exponent to 2.3728596. Look at how close that is to the previous result. Okay, I'm going to zoom out here. So, here we go. That's our timeline so far. Do you think that this is the end of the story? Probably not. I don't think that's the end of the story. I don't think that this method by Ullman and Williams I don't think that that's the true best way to multiply matrices. I think that the true best way hasn't been discovered yet. And who knows, maybe by the next time I teach this, maybe I will need to update this list. Maybe I'll update the description in this video if I find out anything new. But as of today, this is the best known result. Now, I should tell you, some of these algorithms, some of them are not very practical due to a very large number of additions or subtractions, or due to a very large amount of memory needed during the algorithm, like a very large amount of computer memory. So I've heard that the method by Ullman and Williams, I've heard it referred to as a galactic algorithm, and the idea is that it only is practical for astronomically large problems, and that those are not the kinds of problems that we deal with on a day-to-day basis. So it's not the most practical method, and it's probably not going to be used for actual problems. However, it is still very interesting from a theoretical standpoint, even the ones that might not be as practical. Yeah, I mean, it's kind of, there's kind of two sides to this question, right? There's the practical sense of we would like to solve problems efficiently, and then there's the theoretical side that's just curious about what's the best way that something can be done, just because that's interesting. So it was surprising to some people when Strawson found that you could do this with less than omega equals 3, and look at how much lower it's gotten since then. Remember earlier I said that fact number 1, here, earlier, we said that omega has to be at least 2. This was fact 1. So looking at this table, do you think that we're heading towards an algorithm where omega is going to get close to 2? It seems like in recent years, 2.37 something has been as far as we've gotten. Is it going to get all the way down to 2? Nobody knows. I'll say that it could be. It could actually be not just n to the omega like we've been saying, but it could be n to the omega plus some smaller terms. That's something that I didn't address earlier, but you know, we said that it uses n to the omega multiplications. It could be n to the omega plus something smaller, like plus n. Or it could actually be like a constant times n to the omega plus smaller terms. For some coefficient c. This becomes more relevant as you get to some of the more modern methods. In computer science, people are really more focused on just the exponent, though. It's kind of like when you have a polynomial, you want to know what's the degree of the polynomial, right? You want to know what's the highest exponent that appears, because that's the most significant part of it. And yeah, so people are mostly just interested in what is omega. I'll tell you that there are some lower bounds that have been found. I mean, you could say that everything in that timeline is kind of an upper bound on omega. The true omega is less than or equal to these results that have been found, but there are lower bounds as well. So Brockett and Dobkin in 1978 found that omega is greater than or equal to 2n squared minus 1. So that seems to suggest that omega could actually be 2 with this extra terms. And Blasser, I'm not sure if I'm saying that right, but Blasser in 1999 proved a lower bound of omega greater than or equal to 5/2 n squared minus 3n. So people are actually approaching this problem from the other direction. Instead of trying to find an upper bound, they're finding lower bounds on what omega might be. Oh, you know what? Actually, I apologize. I shouldn't say omega here. The exponent is 2, okay? The exponent here is 2. The exponent here is 2. I didn't really mean omega. What I meant is this is a lower bound on the number of multiplications. The number of multiplications is greater than or equal to this, and greater than or equal to this for n by n matrix multiplication. So I've kind of said this out loud, but I want to write this in our notes. Does an algorithm exist with omega equals 2? If that's sort of the theoretical, maybe it can get that low, but we know it can't get any lower, does it actually exist? Well, as of right now, we just know that the true value of omega is somewhere between 2 and 2.3728596 from that method from Ullman and Williams. And this method will probably not be the end of this story. I'll tell you some other active research that's happening in this area. What about rectangular matrices? Everything we've said so far today was about n by n matrix multiplication. And yeah, square matrices are very important, but what about rectangular matrix multiplication? Are there efficient ways to do that? That's being studied. Here's another question. Are there more efficient methods if we know A or B are in some specific form? For example, let's say we are interested in solving problems where we know that A or B has like a specific entry that's guaranteed to be 0. If you know that there are some 0 entries in A or B, can you come up with a more efficient algorithm for those types of problems? Maybe there are some matrices A or B that show up in some real-life application, like maybe there's a physics problem or something like that where A or B have a certain kind of structure to them. Maybe they have some entries that are repeated or some kind of pattern. For those types of problems, can you come up with a method that's more efficient? Here's another question. Can we approximate a matrix product using fewer multiplications? So we've been talking today about trying to get the exact answer, trying to get the exact correct answer. But maybe for some real life problems, you have really large matrices that you want to multiply And maybe it's okay if you just get the answer within 1% accuracy or something like that. You know, maybe it's some real life thing where you just need the answer to be approximately correct, and that's good enough. It turns out that Schoenhag, who was on the timeline earlier, Schoenhag found a way to approximate 3 by 3 matrix multiplication using only 21 multiplications. That was in 1981. I did not include that on the list because the list was interested in getting the exact answer. But this is a different type of problem, and people are studying this as well. All right, so I guess one of the things that I wanted to just get across to you is that this is a very active area of research, and there's still a lot of open questions. And the most recent result was, I believe, just about 1 year ago from the time I'm making this video. So definitely an area where people are coming up with new stuff. All right, so that is efficient matrix multiplication. This lesson was meant to just give you kind of an overview of this topic. I think you can see that this is a pretty active area of research. New things are still being found. I'll tell you that I didn't learn about this problem until I was in graduate school, and I've tried to research it on my own. I've never found a new algorithm or anything like that. It's a tough problem. But basically, I didn't learn about it until grad school, and I thought that it would be a cool topic to include here in linear algebra because, fundamentally, it's just about matrix multiplication, and we understand what that is. It has aspects of computer science because computer science tries to look at algorithms and computational complexity, like what are efficient ways to do things. So, it's kind of at the intersection of math and computer science. But anyway, I think it's really cool. I hope that you liked it too. And that's going to be it for now. So, everybody take care.